Redox processes. High level 1. Electrochemical cells, Voltaic cells and EMF. Essential idea: energy conversions between electrical and chemical energy lie at the core of electrochemical cells. Nature of science. Employing quantitative reasoning. For example, we use electropotentials and the standard hydrogen electrode in calculations. Collaboration and ethical implications. Scientists have collaborated to work on electrochemical cell technologies and have to consider the environmental and ethical implications of using fuel cells and microbial fuel cells. Voltaic cells and voltage. The voltage generated in a voltaic cell is called the cell potential, or the electromotive force, EMF. The little star here is there because voltage is also known as potential difference. The symbol for cell potential is E, capital E, with a small subscript cell. Units are V for volts. Let's consider a zinc copper voltaic cell, and there's an image of there at the bottom left. The zinc is more reactive and loses electrons more readily than copper. Copper is less reactive and loses electrons less readily than zinc. So there is a difference in the electric potential at each electrode. This causes movement of electrons, or an electromotive force, EMF, which is in this case 1.1 volts. Different half cell combinations give different voltages. You can see a reactivity reactivity series over here. And the voltage, EMF, cell potential generated by a voltaic cell depends on the reactivity of the metals in the half cells. Let's have a look at some of the theoretical values for the cell potential produced by different combinations of half cells. So we've got magnesium and zinc at 1.61, and then magnesium and copper at 2.71 volts. Over here we've got zinc with a few different metals. Let's have a look. We've got zinc and nickel at 0.5, then zinc and copper at 1.10 volts, and zinc and silver at 1.56. You can see they're increasing. What do you notice about the magnitude of the cell potential and the metal activity series? It's fairly straightforward, isn't it? The bigger the gap between reactivity series metals, the larger the cell potential. So obviously zinc silver is larger than zinc to nickel. Let's have a look at this list here, standard electropotentials. There's table 24 in your data booklet. A quantitative measurement of the reactivities of electrodes is given by its standard electrode potential, and they're all listed in table 24. All written as half reactions in half cells. All half reactions in half cells are reversible, and by convention the equations are written as reduction reactions. So all the half reactions in table 24 are written as reduction reactions. And the electrode potential represents the tendency of a half cell reaction to undergo a reduction when combined with a standard hydrogen electrode, an SHE. The standard electrode potential of metals are relative to the standard electrode potential of the SHE, defined as it's 2 hydrogen ions with 2 electrons in a reversible reaction with hydrogen gas, and its cell potential is 0. So definition time. This is one for a flashcard, methinks. The standard electrode potential, E, is the electromotive force generated between a standard hydrogen electrode and a metal immersed in a solution containing metal ions at a concentration of 1 mole per decimeter cubed at 298 Kelvin and 100 kilopascals. Standard hydrogen electrodes The internationally agreed standard reference electrode is the standard hydrogen electrode. And as we know, because we just looked at it, this is the equation associated with it. Hydrogen behaves as a metal, it's the reducing agent. The electrode is made of inert platinum wire and is the site of the reaction between the hydrogen ions and hydrogen gas. The electrolyte is a strong acid, such as hydrochloric acid or nitric acid or sulfuric acid. The electrode potential of any half cell is measured by connecting it to a standard reference electrode and measuring the cell potential. Say if we've got metal X, you connect it to a reference electrode, and the electrode potential of X equals the cell potential. The electrode potential of the reference electrode is assigned a value of 0 volts. So our SHE is 0 volts. All metals are measured relative to this same reference electrode. Why did I go forward? Sorry. So the SHE has an electrical potential of 0 volts under these standard conditions. 298 Kelvin, 100 kilopascals, 1 mole per decimeter cubed. But do note that this is the ion concentration, the hydrogen ion concentration, not the acid concentration. So it makes no difference for like HCl or nitric acid, but for H2SO4, 1 molar H2SO4 is actually 2 moles of hydrogen ions. So you'd have to use 0.5 molar H2SO4 to get 1 mole of hydrogen ions. The significance of negative and positive cell potential values. Let's have a look. We've got zinc here, which has a negative value. And a negative standard electrode potential for metal ion half cell means that the metal ion half reaction is less likely to undergo reduction when connected to an SHE, and the oxidation reaction will be favoured. So the metal will undergo oxidation when connected to the SHE and will be the anode. So oxidation is going to happen with the zinc, and reduction will occur in the SHE as hydrogen gas is formed, and the inert metal in the SHE will be the cathode. You see hydrogen gas being formed at the platinum, and the electrons will be moving from the zinc over to the SHE in this case. Significance of significant of positive values. Significance. A positive standard electrode potential for metal ion half cell means that the metal ion half reaction is more likely to undergo reduction when connected to the SHE, and the reduction reaction will be favoured. The metal ion will undergo reduction, and the solid metal will be the cathode. And so copper ions are going to be reduced to copper metal, and the oxidation will occur in the SHE, and the hydrogen gas will make H plus ions, and the inert metal in the SHE will be the anode. You can see electrons there going from the SHE to the copper electrode. Okay, let's look at a couple of questions regarding the significance of negative and positive cell potential values. Given this half reaction, nickel ion with 2 electrons given nickel solid, it's got a negative cell potential. So if it's got a negative cell potential, we know the metal is going to be oxidized, isn't it? So A isn't going to be any good for us, because we know that the metal is going to be oxidized, so this one is correct. Let's just check here. Hydrogen ions in the SHE will be oxidized to form H2. Well, the H plus ions are actually being reduced there, so that's wrong. And the nickel metal will be the cathode. We've just said the nickel metal is going to be oxidized, and if we remember anox, then thing being oxidized is going to be the anode, not the cathode. That's wrong. Nope, the cross didn't work. Next one, we've got silver going, silver ions be reduced, positive this time. And so if it's positive, we know that the metal is going to be reduced. So it doesn't actually give us that option in the first two. Hydrogen will be reduced to H plus ions. Hydrogen will be reduced to this, and it's not being reduced to this, it's being oxidized, so that's wrong too, which means the last one must be correct. If we know the metal is being reduced, the red cat, and the silver metal will be the cathode. So there we go. Okay, we're going to use information from table 24 to identify strengths of oxidizing agents and reducing agents. Let's have a look. We've got the hydrogen, SHE, standard one there, cell potential 0. On the right hand side, we've got mainly the metals there, we've also got some hydrogen, sulfuric acid. The substances on the right are listed in order of decreasing strength as reducing agents. So the very reactive metals at the top and the less reactive metals at the bottom. And so the very reactive metals are strong reducing agents. So the top end there are the strong reducing agents, and at the bottom the weak reducing agents. On the left hand side in that green box, we can see substances here are listed in order of increasing strength as oxidizing agents. It's going to be the opposite. So you've got the weak oxidizing agents at the top, and you've got strong oxidizing agents at the bottom in that direction. So using that table, and you should go to table 24 in your data booklet, you can try and answer these questions. Press pause and give it a go. Okay, which substance is the strongest reducing agent? It is, of course, D. Shall I circle these here? I'll put a line underneath. Which substance is the strongest oxidizing agent? If you got C, you'd be correct. And then, true or false, hydrogen gas is a stronger reducing agent than metallic ion. You should have got false. My pen isn't working too well today. B, hydrogen ions are stronger reducing agent than zinc ions. You should have got that one to be false. And here you see at the very bottom of your table there, this is true, and the iron 2 ions are in the middle somewhere, so obviously they can both reduce and oxidize depending if something's above them or something's below them. So this is true. Okay, calculating cell potentials and predicting spontaneity. We're going to use table 24 to predict cell potentials. Here is example 1. We've got iron with some silver ions, and we're going to calculate the cell potential under standard conditions for this reaction. Write the half equations first for the two, for the iron and the iron add silver ions. We're going to find the electrical potentials. We're writing down. You notice obviously that we're writing an oxidation here, and we're only given reduction reactions in the table, so you've got to reverse the sign. Okay, you'll get used to doing that. And then here we just scribble it straight down, but notice what we haven't done. It says 2 here, but we did not multiply by 2. You do not multiply according to the coefficients. You just put the value in from the table, and then you just add them together. And here we've got plus 1.25. Very straightforward. Reactions with positive cell potentials are spontaneous. Positive cell values are spontaneous. Let's predict the cell potential under standard conditions for this reaction. We've got nickel and zinc ions. So write those half equations down. Look at the cell potential. Obviously be mindful for the positive. It's got to be changed. You've got to reverse the sign because it's oxidation. And then scroll down over for zinc. Add them together. You can see this time it's negative. Reactions with negative cell potential values are non-spontaneous. We're going to use table 24 to predict another cell potential. Here's an alternative method for predicting cell potentials. I prefer the other way, but there you go. Let's have a look at this one. It's a simple formula. You've got the cell potential equals the cell potential of the reduction half cell minus the cell potential of the oxidation half cell. So let's predict the standard cell potential for spontaneously running magnesium and zinc voltaic cell. Oxidation half cell equals the half cell with the more reactive metal, which of course is magnesium. So the reduction half cell is the less reactive metal, zinc. So we can put those in. We've got the cell potential for zinc minus the cell potential for magnesium. And you just write it in from the table, do the maths, and you get your answer. Very straightforward. Do remember this, that electrons always tend to flow to the half cell with the highest standard electrode potential value in a spontaneous reaction. The half cell with the highest standard electrode potential, i.e. the most positive cell potential, will undergo a reduction. Electrons flow towards the site of reduction. And the half cell with the lowest standard electrode potential, the most negative cell potential, undergoes oxidation. Electrons flow away from the site of oxidation. Okay, again, have a look at table 24 as we do this. We're going to predict the equation for the spontaneous reaction that occurs in a nickel-silver voltaic cell. The metal with the more negative electrode potential is the more reactive, and so it is oxidized. And you've got to make sure, remember it's oxidized, you've got to change the sign. And so we're going to have plus 0.26 volts. The metal with the more positive electron potential is the site of reduction. Its ions are reduced, so the equation is written as given. And you don't need to change any signs there. You can put the two equations together and add the cell potentials together. You can see it's positive, and so we know that it's spontaneous. What about with lead and iron? So again, the metal with the more negative electric potential is more reactive, so it's oxidized, and you've got to reverse it from that table and make sure you're careful with that sign as well. It's got to be reversed. Then the metal with the more positive electron potential is the site of reduction. Its ions are reduced, so the table is written as given. And so it is written as given, should I say. There we go. Let's add those equations together, and then we can add the cell potentials together. I'm just going to move this along. Okay, plus 0.32, so it's positive, and therefore spontaneous reaction. Another one, reactions between chlorine, aqueous chlorine, and iron 2 plus. Again, substance with the more negative electrode potential is oxidized, and reverse it, so stick it in there and make sure you're careful with the negative value. The substance with the more positive electron potential is the site of reduction. It's reduced, so the equation is written as given. Add those equations together, add the cell potential together, it's positive, so it's a spontaneous reaction. What about this one here? We've got half equations and electrode potentials given. They're not on the table. We're going to predict the spontaneous equation that will occur. And we're going to identify the oxidizing agent and the reducing agent. Okie dokie. So the substance with the more negative electrode potential is oxidized, and we have to reverse the equation. So we'll put the chlorine equation in, spin it around the other way, and we have to change the sign, obviously, from positive to negative. Next, we've got the more positive electron potential equation. We write down the cell potential, add all of the add the two equations together, remembering to cancel the electrons, and cell potential added together, 0.20. The MnO4 minus is the oxidizing agent, and chlorine is the reducing agent. And you can see that straight away. A simple way to do, of course, is you can see this is being oxidized. and if it's being oxidized, it must be the reducing agent. Okay, here's a few nice little rules to remember for when you're predicting cell reactions. If you've got the table 24, you can kind of just look at it and see relationship to see whether a reaction is spontaneous. Reactions between a relatively strong reducing agent and a relatively strong oxidizing agent will be spontaneous. And you can see it's going to look like this. You're going to have something high up on the right hand side and something low down on the left hand side. Okay, and so basically if you've got something with this line, if you circle the two things, it's going to work. Predict the reaction between calcium metal and aqueous tin nitrate. You can write down the two equations, add them together, but obviously a strong reducing agent and a strong oxidizing agent is going to work. It's going to be spontaneous. Next, reaction between a relatively weak reducing agent and a weak oxidizing agent will not be spontaneous. So if the relationship is something high up on the left with something low down on the right hand side of the table, it ain't going to work. And so you won't get spontaneous reaction. In this reaction, electrons would flow from the tin half cell to the calcium half cell, which has a more negative electrode potential. The reaction isn't going to be spontaneous. And here, this one's more straightforward, I guess. It's just common sense. Reaction between two reducing agents or two oxidizing agents isn't going to occur. So if you're going to try to predict the reaction between tin metal and calcium metal, there's going to be no reaction. Both metals act as reducing agents, and a spontaneous reaction must have both an oxidizing and a reducing agent. In the same way, if you've got tin 2 ions and calcium ions, you get no reaction. Both metal ions act as oxidizing agents, and a spontaneous reaction must have both an oxidizing and a reducing agent. Okay, predict whether or not each of these reactions is spontaneous. For any spontaneous reaction, you can state the overall net equation and the two half equations. Well, the first one has got iron and lead, and you can see, you can't really see it on this, can you? I think iron was around here, isn't it? There it is. Iron's there, lead's there. So it's like this one, isn't it? Iron and lead. So it isn't going to occur. Potassium permanganate and sodium iodide. Now this is, you have to look in your data book for this. I can't just flick back to it on that table. But this is a very, very strong oxidizing agent, and the iodine ion is kind of somewhere in the middle, and so you're going to get a spontaneous reaction here, and you can just copy down the two half equations from your data table. Okay, cell potential and free energy change, delta G. We've got standard free energy change in joules, and equals the moles of electrons transferred. We've got Faraday's constant, and we've got the standard cell potential, joules per coulomb. Recall that delta G values are used to predict the spontaneity of a reaction. We've seen that cell potential, standard cell potential, can also indicate the spontaneity of the reaction. It's a bit different though, isn't it? Because the standard free energy change, if that's negative, it's spontaneous. The reaction is spontaneous when it's negative, and it's non-spontaneous when it's positive. Conversely, with cell potentials, a positive value is spontaneous and a negative value is non-spontaneous. Okay, let's have a look at an example. I'm going to calculate the standard free energy change, delta G, for copper nickel voltaic cell operating under standard conditions. So we're going to predict the equation and find the cell potential. Nickel is the more reactive metal, so it's oxidized. Copper 2 ions will be reduced. So we can write down the oxidation of nickel there and scribble down the potential, and then do the same for copper, both from your table. Add the equations together and you can add the cell potential together to get a positive value. Okay, now we calculate the standard free energy change. Stick in the equation, remembering your negative sign. We've got 2 moles, put in your constant, we've calculated the cell potential, and then just calculated, get a negative value, so you know it's going to be spontaneous. What factors affect cell potentials? Well, the nature of the electrodes does, the temperature that occurs at does, and the concentration of electrolyte does. And that's why we have to have these standard conditions when we're calculating the cell potential. However, if you're not under standard conditions, you can use something called the Nernst equation. And don't worry, this is not included in your exams. However, some of you might want to do internal investigation using this. It's kind of straightforward, but it allows you to predict cell potentials under non-standard conditions. And you can see here, it's kind of plug and play. Okay, you would just put in the temperature, you put in the moles, you get equilibrium expression using given ion concentrations there. Okay, but you needn't worry about this unless you plan to do an IA on it. And that's the end of that presentation. Splendid.